How can we tell different kinds of matter apart? Well, we can look at their chemical or physical properties. We had an example when we were talking about density about the gold pebble, the gold-colored pebble, and how do we know, is it made out of gold or not? And we calculated its density and compared its density to that of gold. Density is a physical property of substances. Different substances have different densities. A physical property is one that a substance displays without changing its composition. Chemical properties are those that the substance displays only through changing its composition. So when you demonstrate a chemical property, you destroy the substance. You can demonstrate a physical property without destroying the substance. So let's think about gasoline. Gasoline has a very distinctive smell. The smell of something is a physical property. Gasoline giving off its characteristic smell does not destroy the gasoline. It's still gasoline. Gasoline is also flammable, which is why we put it in our cars, right? That's a chemical property, that it burns. When we demonstrate gasoline burning, we destroy the gasoline. It gets burned up. So with a physical property, the individual pieces, the atoms or molecules, aren't being changed. So anytime we have a physical state change, melting, boiling, freezing, those sorts of things, the particles are not changing, and so that's a physical property. The boiling point of water, 100 degrees Celsius, that's a physical property. We can demonstrate that water boils at 100 degrees without destroying the water. They say, yeah, but the water went away. Well, it did go into the gas state and dissipated into the room, but the individual water molecules are still water molecules. Here's a picture of that. So here's a pot, coffee pot looks like. And we've got these little water molecules, and we're heating it and boiling it, and they go into the gas state, but they still are they still are water molecules. So that's a physical property. A chemical property, though, the particles change. Here we have a nail made out of iron, and it's just a bunch of iron atoms all hanging together. When it rusts, it combines with oxygen, and now the particles are changing. The particles have changed. Now we've got oxygen and iron in there, and this is not going to be the same anymore. So determine whether each of these properties is physical or chemical. The explosiveness of hydrogen gas. Chemical or physical? Chemical. Anything exploding, burning, anything like that. The bronze color of copper. That's physical. That's its appearance. You look at the color of it, it doesn't change what it is. The shiny appearance of silver. Physical. How about the ability of dry ice to sublime, which means to change directly from the solid to vapor? Physical. That is a state change. It's a weird state change. It's a crazy state change. Most things don't do that. Most things melt first and then go to the gas. But it's just a state change. When you guys leave the room, you go from right now in the solid state to the gas state, but each of you individually stays who you are. You don't become different people or split into two halves or anything crazy like that. We've got physical and chemical properties, and those are very closely related to physical and chemical changes. So anytime we have a state change, we have, it's a physical change. The physical property is the temperature at which it happens, or the fact that dry ice does that. It changes directly from the solid to the vapor, the gas state. That's the property. The physical change is when it actually does that. So the physical property, physical change are really similar. Sometimes it's hard to distinguish which one's the change and which one's the property. When you have a physical change, the matter may change in appearance, but its composition doesn't change. When you have an ice cube and it melts, the particles are the same. It's changed its shape. Now it's runny, and if you throw an ice cube at somebody, that kind of hurts. If you throw water at them, they get wet and they might get mad, but it doesn't really hurt, right? So the properties of the matter have changed somewhat, but the individual particles are still the same, and so that's considered a physical change. So any state change is a physical change. In a chemical change, you do have the matter changing its composition. Copper turns green upon exposure to air. So you get a bright, shiny copper penny, and you leave it outside for, I don't know how long it would take, weeks probably. It's not going to stay bright and shiny anymore because the copper reacts with oxygen and moisture in the air, and it forms a new compound, and it's kind of greenish in color. And that's a chemical change. A chemical change and a chemical reaction are the same. A chemical reaction is a chemical change. A chemical change results in the substance being changed. And so we have what we start with, we call those the reactants, and what we end up with are called the products. So the reactants react to produce the products. You start with one substance, you end up with something else. And that's called a chemical change. There's a lot of words on that slide. So this is saying it over and over again. Chemical change, the individual particles change. Physical change, the individual particles do not change. Let's look at this butane lighter. So here you've got butane in here. And if you just flick it without actually lighting it, the butane will start to come out. You might not notice it, but the butane will come out. These particles look just like the ones in here. All that's happening is that it's evaporating. It's going from the solid liquid state to a gas state. That's a physical change. The individual particles are still butane. If you flick it and actually light it, now you've got combustion, you've got a chemical reaction going on here. The butane is being burned, and it's being converted into carbon dioxide and water. It's not the same thing anymore. That's a chemical change. Determine whether each change is physical or chemical. The rusting of iron, chemical. It's chemical because the substance is changing. Evaporation of fingernail polish remover, acetone, from the skin. Physical. The clue there is that word evaporation. That's a state change. The burning of coal, chemical. Burning, exploding, reacting, all chemical changes. The fading of a carpet upon repeated exposure to sunlight. That's a chemical change. That's not obvious, is it? The sunlight causes a change in the pigments of the carpet and causes it to change color. And that's a chemical change. We can use physical changes and physical properties to separate mixtures. So this is an example of distillation, which separates liquids or a liquid from other solids based on differences in boiling point. So perhaps you had a mixture of liquids here, maybe alcohol and water. And if you heat this up, the water is less volatile than the alcohol. The alcohol has a lower boiling point. And you can see that if you put like rubbing alcohol on your hand, on one hand and water on the other, the alcohol feels colder, doesn't it? Because it evaporates much faster. The alcohol will boil at a lower temperature. So it will boil, it will go into the gas state, but we're going to trap it and bring it through this condenser, which has cold water running through it. We're going to cool it down. We heated it up to get it into the gas state, and then we're cooling it down, and it's going to go back into the liquid state, and it's going to run down here, and we're going to collect it. What's left over here is the less volatile liquids. And so this is one way that you get distilled spirits. You know, where does vodka come from? Well, it comes from the vodka store, right? Well, no, they take, and I know a little about alcohol. They, you know, like for wine, you take grapes and you squish them up and you either put bacteria, yeast stuff in them, or you count on the natural stuff that was on the grapes. They will ferment, and the organisms will convert the sugar into alcohol. But do you necessarily want to drink the whole big mess? Well, maybe not. And when they make distilled spirits, they make alcohol by fermenting some sort of a product, whether it's, you know, barley or hops or wheat or whatever, and then they distill it to get the alcohol out and get it more pure. And so it's stronger than if you just left it all together. And that's separating things based on the differences in their boiling points, which is a physical property. When you distill something, you don't change what's in it. You can distill water. Distilling water will separate it from many minerals and things that might be in it, and you can get more pure water by distilling it. Another way to separate mixtures is by filtration. We got two things, and maybe one's a solid and one's a liquid, but they're mixed up together. Like you make coffee. One way to make coffee is just to pour the coffee grounds into hot water. Stir it up. Look, there's coffee. It's got all those nasty grounds floating in it. How do you separate them? Well, your coffee maker has a coffee filter on it, doesn't it? It's a paper cone, and the coffee ground water mixture goes through there. The paper filter allows the water with all the coffee goodness in it. Not that I like coffee, but my husband likes it, so I know that most people consider it to be wonderful stuff. All the coffee goodness to come through, and all the nasty ground up pieces of coffee beans stay back in the filter. Same thing when you cook spaghetti. Get a big pot of water, you throw the spaghetti in there, it's done cooking, you want to get the spaghetti out of the water. Yeah, you can use a slotted spoon or a fork or something, but it takes a really long time, doesn't it? What do? You dump it in a colander, which is basically a bowl with holes in it. The holes let the water out, but they're too small to let the spaghetti out. So we're separating a mixture of water and spaghetti based on differences in their states. One's a solid and one's a liquid. So there's lots of different techniques for separating mixtures. You cannot separate a compound using any of these techniques, because in a compound, all the pieces are the same, and so you can't separate them.